What if we wanted to add together 2 square roots of 3 plus 3 square roots of 3? Well, as it turns out, that's just 5 square roots of 3. It's just like back in the days when we had, say, 2x's plus 3x's, and we added them together to get 5x's. We could add these terms together because we called them like terms. And in a sense, that's really exactly what we're doing here. In fact, we call these things like radicals. Before, like terms had to have the same variables with the same powers on them. Like radicals have the same index, that's this number right here, whether it's a square root or a cubed root or a fourth root, etc. That's the index. They have to have the same index and they have to have the same radicand. And again, the radicand is the technical word for what's under the square root. So here's an example. Let's take the square root of 20 and subtract 7 square roots of 5. Well, our index is the same. Both of these are a square root, but the radicands are different. So it kind of appears like there's nothing we can do here. However, the square root of 20 can be simplified. 20 can be split up into 4 times 5, and the square root of 4 is just 2. So we have 2 square roots of 5 minus 7 square roots of 5. Now we have our like radicals here, and you just take 2 minus 7 to get negative 5 square roots of 5. Well, there's not much we can do at this point except get a little bit more complicated. Let's see if we can combine these two roots. The index is the same, they're both square roots. We have an n to the 5th under each of the square roots, so that's a good sign. But the 50 and the 32 are different numbers, so we can't immediately combine these two square roots. Let's reduce each of them though and see what happens. We want to pull a perfect square out of 50n to the 5th. Well, 25 is a perfect square, as is n to the 4th. What's left is a 2n. How about on our second radical? 16n to the 4th is a perfect square, and that would leave us with a 2n here as well. If we reduce 25n to the 4th, that's just 5n squared, and the square root of 16n to the 4th is 4n squared. Okay, now these are like radicals. We have the square root of 2n and the square root of 2n. Our coefficients are 5n squared minus 4n squared. 5 minus 4 is just 1, so you just get 1n squared square root of 2n. Now in this example, you'll remember that we can split up factors under a radical into two different radicals. So we can split radicals into two pieces, but we can also multiply radicals together. If we have the same index on our radical, we can multiply them together just by multiplying what's inside. Cube root of 18 can't really be simplified any further, so let's look at another example. If we have 6 square roots of 2 times 2 square roots of 5, you can multiply the numbers together first, and then multiply the radicals together. And again, the square root of 10 can't be reduced, so we'll just leave it as it is. Okay, how about 5 cube roots of 4 minus 2 cube roots of 6? Again, I'm going to multiply the numbers out first to give us negative 10. These roots have the same index of 3, so we can multiply the 4 and the 6 to get 24. This can be reduced. 24 can be written as 8 times 3, and 8 is a perfect cube. The cube root of 8 is just 2. The cube root of 3 can't be reduced, but then we can multiply the 10 and the 2 together. You end up getting negative 20 cubed roots of 3. Okay, let's do one more example and then we'll end the video. Let's multiply these two binomials. And the rules don't change just because we're dealing with square roots instead of x's. We're still going to distribute this out. 2 times 4 is 8. 2 times negative root 3 is negative 2 root 3. Square root of 2 times 4 we usually write as 4 square root of 2. And the square root of 2 times negative square root of 3 is going to be negative square root of 6. Now, if this was a more well-written problem, we might be able to combine some like terms here, but none of these are like terms, and none of these are like radicals. So that is just the answer. Okay, that's all I got for now. I'll see y'all in class.